So our second speaker today is Allessandro Sisto, and he will talk about Markov chains on groups and quasi-isometries. So please.
All right. Thank you very much for the invitation. Very happy to give this talk. I'm Alessandro, and my quasi is quasi-isometries. So I'm not 100% sure about the background of the audience, so please do feel free to interrupt me at any point. I'm very happy to explain more. And I guess I should start by asking if I should define K graphs and quasi-isometries, or
just go ahead. You know, we will interrupt you if we have.
Okay. All right. So let me share my screen. And so right. So there's one main idea that that I would like to advertise with this talk, and it's something that's been it's pretty recent. Maybe less than 2 years ago there was the first paper kind of exploiting this idea, so this starts from so this story starts with two things I like, but it's at the beginning it's a sad story. So even though it starts with things I like. So one thing I like is random walks. All right. So I won't give the formal definition, because I think that the informal definition is more, is much clearer than the formal one. And I'm sure that you, even if you haven't seen this before, I'm sure that you will have a good idea of what a random walk is in just a minute. So what's a random walk? You have on a group, I should say. So you start with a group and a finite generating set of the group. So every group element can be written as a product of these elements of S, and let's say that S is finite. And the random walk starts at the identity. So the identity of this group, and I'm gonna write it as the position at step 0. So W is denotes the position. As the position at step 0 is the identity. Then at each step, so you will take various steps of this random walk, and you will move from where you were at step n. So from Wn, let me denote the end where you are at step n by G, to the n+1 position, and which is going to be of the form G times some of the generator. Okay, for S in S. And how do you decide which S this is? Well, you kind of don't decide. You say I choose it uniformly at random. So chosen uniformly at random. All right. So what is this sentence actually describing? It's describing a sequence of probability measures on your group, which describe how likely it is that you are at any given particular element of your group. So this and some random variables Wn with those distributions. All right, so maybe a little picture. It's just that you start at the identity, that's W0, and then you have in your KD graph you have various edges coming out of the identity, each corresponding to one of the generators. That's how KD graphs are defined. And so you say that you pick this one, and then maybe from here you have various other choices, and then you will pick this one, and so on, and you end up with certain probabilities, some group elements, some other probabilities, some other group element. All right. So this have been studied at least since like the 50s or even more on groups, and of course in Brownian motion, it's related to Brownian motion and other probability things that have been well studied for a very long time. All right, so the other thing I like are quasi-isometries. So my quasi is quasi-isometries. So I like to think about quasi-isometric groups and what what you can say about quasi-isometric groups, or also trying to say that this group cannot be quasi-isometric to this other group. So that has been a large part of geometric group theory for a few decades now. Just trying, saying classifying groups up to quasi-isometry is not quite right. I mean, you cannot quite do that, but going in that direction. All right. So I told you it is a sad story. So why is it a sad story? Well, there's these two things I like, but they really don't talk to each other very much. So there's not good interaction between these two concepts. So if you have a homomorphism between groups, you can push forward a random walk via this homomorphism, and that's a useful thing to do. It gives you, if you have knowledge about random walks in one of the two groups, you can deduce something. There's something that you will deduce, and of course, if you have isomorphic groups, then random walks behave the same. But there's no such thing as the push forward of a random walk by a quasi-isometry. There just isn't. And so you might have a group for which you know absolutely everything you want to know about random walks, and a group quasi-isometric to it, and you don't know basically anything about random walks on that group. All right, so that's so the main idea I want to advertise is that maybe it's worth studying not just random walks, but more general random processes. So random walks are a special case of Markov chains. So what's the difference between random walks and Markov chains? Well, instead of having this fixed set S and that everywhere you are in the group, the next jump is determined, is chosen uniformly at random from S, you just decide for each group element a different set of possible jumps. Okay, so that's the only difference. The set of jumps depends on the group element. Right. So you were.
But you also want to make it then uniformly at random for the choice for each group element.
Right. So I was gonna say that yeah. So one thing I forgot to say is that this is actually the description of what's called a simple random walk. Whenever I say random, so for simplicity, I'll just stick to that. So whenever I say random walk, assume that I mean a random walk of this type. You could have different probability measures on your group, not just a uniform measure on a generating set. And also for Markov chains, you could have different probability measures on at different group elements, not necessarily uniform over finite sets. Okay, but let's stick to the simplest types of cases. So right, so where once again what the jumps do depends on the group element G. So maybe at some group element G you can jump a bit further, and some other element H not you cannot jump as far. All right, so let's see. So would this actually help us? So the observation is that if you have a map between groups which is now a bijection, I guess injection would be enough. And a Markov chain, including a random walk. So for example, a random walk on G then let me write it informally, because I mean I would have to tell you the exact definitions of this thing to make a formal statement, but I think you will see what I mean, that there exists a Markov chain push forward of Wn on H. Okay, essentially all these SG you can push forward, and you have a corresponding set, and the two random processes are linked by this map F. So maybe you start with a random walk and you get something that's no longer a random walk. So that's why you need Markov chains. But there's a bad word here, bijection. So I said that I'm interested in quasi-isometries. Why am I talking all of a sudden about bijections? Well, there's a theorem of White which says that if you have G and H non-amenable, so let's just say groups that contain some free subgroup that's good enough to be non-amenable, and you have a quasi-isometry between them. Quasi-isometry. Then there exists a bijective quasi-isometry between them. Let's call it F bar from G to H. And in fact, this bijective quasi-isometry is within finite distance of the original one. But in any case, the main point is that if two groups are quasi-isometric, two non-amenable groups are quasi-isometric, then they are quasi-isometric. I mean, then there is a quasi-isometry which is bijective between them.
Can't you even say that you have a bi-Lipschitz map?
Yes, so it would be a bi-Lipschitz map with of their word metrics. Yeah. All right. And so now we're happy, at least for non-amenable groups, which happen to be the kind, I mean, all the kind of groups that I tend to like are non-amenable. And we can study Markov chains as a quasi-isometry invariant theory of random walks. So if you study Markov chains, you can say you should be able to study Markov chains on a specific group. You should be able to say interesting things about random walks on groups quasi-isometric to the original group. And that's the main thing that I would like to advertise. So it hasn't been explored so much yet. So there's I guess 3 papers out on this. Maybe a 4th one on it should hopefully be out soon. But yeah, so it's pretty new, and what we can, I mean, how far we can go, I don't know, to be honest. But I think it's worth exploring, and there could be interesting, various interesting things to do in different directions. So what I want to do is just survey what's been done so far. And and it's in 2 possible directions. Maybe there's more possible directions. Those are the directions we could think of. So the first one is what I said in words. Let me write it. So study Markov chains on your favorite non-amenable groups. Groups. And then from that deduce results on groups Qi to your favorite amenable groups. Results on random walks on groups Qi to those. So that's what the first paper in this area was about. And the first one I will talk about. Let me just also tell you what the other direction was, is that we are exploring at the moment, which is constructing random quasi-isometry invariants. So maybe this point of view will allow you to tell groups apart because of different properties of Markov chains. All right. So let's we will get back to this.
Can I quickly ask a naive question?
Yep.
I don't know much about random walks in non-amenable groups. Are there any examples of non-amenable groups where a lot of random walks is already known, or some where there's nothing known at all, like concrete examples that you know of?
So they've right. So for groups acting on, I was gonna get to groups acting on hyperbolic spaces. Interesting ways. There's a lot of a lot is known about random walks on those. And that's kind of also the first thing that we looked into. That's I don't know. Yeah, I would say that's maybe the main right. So where most of the recent, at least the research in the last 10-ish years has been 10-15 years on groups acting on hyperbolic spaces. At least the research I see. Maybe there's other groups that, I mean, there's other research that I'm not aware of. I don't know, does that answer your question? Yes.
Sorry, yes, I was muted.
Yeah.
Yes, thank you.
Sure. All right. So, all right, so part one. So maybe this will not be your favorite non-amenable groups, but they're my favorite kind of non-amenable groups. So another thing I like is when a group acts on a hyperbolic space. So you have a group acts on X. So I think you don't really need to understand these words. So while X hyperbolic, maybe it's good if you know that. If you don't know, you can stop and I'll tell you. These two words are less important, acylindrically plus non-elementarily. It just means interesting enough for the purposes of this talk. And the main thing is that there's lots of examples of this kind of groups. So these are called acylindric hyperbolic groups. It's there are many examples, and we cannot cover all of. So, and for the theory for random walks covers all of them somewhat uniformly. But for Markov chains, we're not quite there yet. So we can only do certain more specific examples. So here are some of the examples that we can where we will be able to say something. So first of all, hyperbolic groups, which act on their Cayley graphs. But also they act on many other hyperbolic spaces. So for example, some Kondorf hyperbolic spaces over quasi-convex subgroups. This will be covered by results that I will mention. There's some generalization of hyperbolic groups which are relatively hyperbolic. So hyperbolic groups are fundamental groups of, I mean, they include fundamental groups of compact negatively curved manifolds. So relatively hyperbolic are meant to capture finite volume negatively curved manifolds, and they have an associated hyperbolic space to them, so it's called also the Kondo space. Then something that hopefully we can get behind is three manifold groups. So fundamental groups of three manifolds, and most of them are they have a hyperbolic space to act on. There's very few that do not, like the ones with solid geometry, for example. But so three manifold groups, right? And then so right angle arcing groups. I mean, if you don't know all these examples, it's fine. Like hopefully you at least one speaks to you. So right angle arcing groups, and okay, in the first paper we needed a separating edge. Soon we will not need it. It looks like, and also right angle Coxeter groups instead of right angle arcing groups, and a separating non-edge, which also we will not need in the very near future. And these are split into, you know, we don't do things separately for all these classes. We have, let's say, an additional assumption besides an interesting enough action on a hyperbolic space. And we have, in fact, two possible sets of assumptions that work with three manifold groups, half of them satisfying one assumption, half of them satisfying the other assumption. And if you want, at the end of the talk, I can tell you more about these assumptions, but I don't think that they're very important because hopefully in the end, no additional assumption will be needed. And maybe if I give this talk in a year, there will be, the sets of assumptions will change. And in any case, they are about to change. There's gonna be another whole list of things that get added here. I'll comment on that in a second. But okay, so what's the kind of theorem that we can prove about all of these things? It's a theorem, I should emphasize, on random walks. There will be no Markov chains mentioned here. So let G be a group quasi-isometric to a group satisfying either one or two. Okay, so for the purposes of this talk, just a group from the list of examples. Okay, and let's Wn be a random walk, meaning a simple random walk. As defined above, on this group G. Okay, the conclusion is a central limit theorem. So the conclusion says that you have very good control on how far you are from where you started at any step of the random walk, kind of as good control as you can expect. So if you do let me write the statement. So the distance in a word metric, so dg denotes a word metric from the identity. So what do you expect this to be? You expect this to be about linear. And what's the variance, the scale of the variance that you expect? About square root of n. Right, and this tends to a normal distribution. So normal distribution. So in words, after n steps, you are in a you are a distance ln from the identity with an error of about square root of n, and controlled with a normal distribution. So that's as good as you can. So what do I forgot to write the names, sorry. So this is with Antoine Gosbra and myself. So it's theorem 3 because it follows from theorem 1, which follows from theorem 2, which follows from theorem 1, which I will tell you later. So those will be results on Markov chains. This is a result on random walks.
So, of course, distributional limits, right?
Yeah. So right. So what do I like? So what should you be impressed about this theorem? So you should be impressed that it starts with let G be QI2. So the only thing you know about this group is that it's quasi-isometric to something. And then the conclusion is a pretty strong conclusion about the random walks on G. All right. Okay. So this is right.
I have a question.
Yep.
Yes, so the results for the groups themselves from your list were already known before?
Right. So that's why I wrote group satisfying assumption 1 or 2, because otherwise there's QI rigidity results of that type. So if you're QI to a hyperbolic group, you're hyperbolic. And then and then you have a previous theorem of myself and Pierre Mathieu, which is a CLT for acylindric hyperbolic groups. So, well, I mean, for hyperbolic groups in particular. And then the 3 manifold groups, I'm not sure that they are QI rigid. They might be, all of them. To finite index. Okay, anyway, so I'm not sure that a group QI2, a group satisfying assumption 1 or 2 is a cylindric hyperbolic, but also the other thing I wanted to mention is this open question, which I'm starting to believe the answer to be, I mean, I used to believe that the answer was yes. I'm starting, I mean, years ago, I started to believe that the answer is no, because no one has any clue how to do it. So let G be quasi-isometric to an acylindric hyperbolic group. So is G a cylindric hyperbolic? So this is not even known if you have a finite index sub. So it's not known that if you have a finite index subgroup which is a cylindric hyperbolic, whether you're a cylindric hyperbolic, which is also another reason why I'm starting to think that the answer is no. And so this theorem, if you want, tells you that you don't, maybe you're not a cylindric hyperbolic, but maybe you have a CLT for random walks, which was one of the consequences of being a cylindric hyperbolic. Right, and yeah,
thanks.
And sure. And yeah, so I like to believe that this thing about Markov chains has something to do with this question, like, you know, that maybe you can use it to prove that the answer is yes, at least in some cases. I mean, I don't know, but I don't have any evidence for it anyway. So yeah, but I like to think that there's a connection with the question. All right. Very good. So let's see, I'm doing fairly well with time. So I want to tell you just one bit, like one thing how one gets here. So where the Markov chains come into play, and so the point is that there's a crucial theorem in the theory of random walks for groups acting on hyperbolic spaces, which is incredibly useful. So it's a theorem of Heriot-Watt, and it says that if you have a group acting on X, which is a hyperbolic space, and the action is just non-elementary even, and you have a random walk, then the random walk makes linear progress in X. So you have your random walk in G. Via the orbit map, you can see what happens in X. That is to say, you can measure the distance in X between some base point and a translated base point by the random walk. And you and the statement, so the statement is that this grows linearly. Well, okay, even the expected value of this growing linearly is a very non-trivial statement, but it says it's even better. So the probability that this is smaller than n times some constant, some large constant, the probability of this is very small. So it decays exponentially. So let me write it as like this. Okay, so there's only a very low probability that you are in a ball of radius epsilon n around the base point in X. So this is good news because you can use the geometry of the hyperbolic space to study the random walk. So if the random walk stayed in a bounded, so with high probability stayed in a bounded region of this hyperbolic space, you wouldn't be able to use the geometry of the hyperbolic space to study the random walk. It's like being hyperbolic is a large scale concept. It only gives you information when you have configurations that are sufficiently large. Right, and so this is usually referred to as linear progress result, and it's a crucial result in the theory because from linear progress you deduce lots of different things. You deduce that generic elements act loxodromic on the hyperbolic space, for example. So something about the translation length of random elements. You can study random subgroups, for example. And also more relevantly for us, you can study something called deviation from geodesics. So how far a random path stays from a geodesic. And that's actually the thing that leads to the central limit theorem. So you definitely want to prove an analog of this result in the context of Markov chains if you want to make up a parallel theory of Markov chains. I mean a theory parallel to that of random walks. And yes, so and then theorem 1 says that this is correct. So let Gx be as in assumption 1 or 2, which I haven't told you exactly what they are, but at least you have some examples. And then we do what we called theorem 1 is same authors. Keep forgetting to write the authors, Galsbra and myself. So a tame Markov chain on G. Okay, so where this tame again is one of those things that if you want, I will tell you at the end of the talk. So the only relevant things are this contain random walks. So this class of Markov chains contains random walks and is QI invariant. But yeah, a general Markov chain is going to be too crazy. So you have to add some assumptions, and as long as I mean, I'm not sure that this notion that we define is going to be exactly the perfect one to use, but any notion that contains random walks and is QI invariant would work. Like it is is a good enough notion to work in this context. Okay, so WNT Markov chain on G, then linear progress. So it's exactly the same statement. You know, I can literally copy paste this thing. There you go. So you're sure that it's exactly the same statement. I just copied it. All right, and so what would be so would be great to do it for all cylindrical hyperbolic groups. That seems out of reach at the moment, because then you will get all the same consequences as well. So from theorem 1, so that's kind of the hard part, and then all these implications here, you can use known techniques. So the thing that requires new techniques is this one. So somehow the proofs, so there are a few proofs of the Heriot-Watt theorem available by now, and somehow none of them work. So we really needed something new, and that's why we also need additional assumptions. But from linear progress to the consequences instead, it's we can reuse the same arguments that were known for random walks. So the thing that I wanted to mention also is work in progress, but it hopefully, well, this month seems excessive, but let's say within a couple of months, hopefully, we should be able to post this on archive. That there are other cases that we can cover.
Can I ask a quick question, just to make sure I understand the statement correctly? Yeah. So what is the quantifier here on the C in the bracket? So there exists a C so that this
yes,
decay holds?
Yeah, exists C for all n, yes.
And you know, the C's on the other side, of course, are different C's, right?
Yeah, so you can, yeah. So I can use the same constant, but they're all non-constructive. So yeah, I mean, I don't know what they are. So maybe this is better. Yeah.
There exists epsilon and C, so that you have this.
Yeah. Okay. Yeah. Okay. So in progress, at least we can do what's called hierarchical hyperbolic groups. And these include mapping closed groups, all right-angle arting groups, all right-angle Coxeter groups, and several others.
So let me ask you another kind of naive question here. This is probably way too much to hope, but could it be that there is a kind of very general class of graphs, so that this linear growth is somewhat preserved under quasi-isometries?
So the I'm not sure that this will answer the question, but if you have a group acting on a hyperbolic space and a group QI to it, there's no hyperbolic space for that group.
But I'm trying to get just maybe a general statement for graphs, right? So you know, you have a graph with some properties, and then you do a simple random walk on the graph, and then you can ask, you know, whether there's some kind of linear growth. I mean, you need a graph that kind of looks like a hyperbolic space, I suppose. Right?
So you will need a graph that maps to another graph, and then you measure distances. So you do a random walk on the first graph, and then you measure distances in this other graph. Yeah, there could be. It would fit better with this. I mean, yeah. So it would fit better with the philosophy that, you know, there's no equivariance. So why would you have a group? Yeah, I think it's a. Yeah, I think you're right. I think maybe this is not the right setup for the theory. Like you should do something better. Right, same for yes, sorry. And we have to change the random walks a little bit, the Markov chains. But they're still contain random walks and are quasi-isometry invariant. Anyway, so I only have 10-ish minutes, so maybe okay, since I wrote theorem 3 and theorem 1, I should write at least an informal version of theorem 2. But as I said, this would be kind of a bit of a different story, because theorem 1 is the hard part, and then from that point on, there's a well-oiled machine that gives you lots of very nice results. So the informal version is that random paths of a Markov chains on our kinds of groups that we're looking at stay close to geodesics in some quantitative sense, and in the Cayley graph, in a Cayley graph of G. So so why is this good towards the central limit theorem? Well, because the distance along the path is then nearly additive. So and that's actually, then there's a criterion for the central limit theorem, which is the one that we used in the paper with Matteo to do acyclic hyperbolic groups that tell you the CLT. But yes, okay, so this part is would be a different talk. I mean, I think it's interesting, but it would be a different talk. All right, so that's what I wanted to tell you about the kind of things that that one can do on, you know, in terms of random walks on groups quasi-isometric to something. I mean, the things that one can do so far. And there was this other direction which actually we barely started to explore it. And I wanted to tell you just very, very briefly about one thing we tried. So there's one, so far we only tried one thing, which is on a related to a quasi-isometry invariant, which is called divergence. And so what divergence measure, I'm not going to be precise, is the following. So you take two group elements in your group, G and H, and they are their distance n. So this is their distance, let's say exactly n, from the origin. And then you want to connect them by a path, but that path you want it to also be, well, you would like to say outside the ball of radius n. That won't really work, because maybe there's no such path, but maybe a ball of radius n divided by 3. Okay, and so that divergence would be the minimal length of a path. So in particular, if you know what the divergence function is, you know that there exists a path with length, as in the picture, with length at most the value of the divergence function at n. And divergence is kind of the optimal function with this property. So for example, you could do, and this you can also do for metric spaces. So you could do the divergence of R square, and then that's about linear. So you can go around the circle in linear time. But the divergence of the hyperbolic plane instead is exponential. So it takes a long time to go around balls. Okay, so this you can turn into, so the class of this, the equivalence class of this function in a suitable equivalence relation is a QI invariant. And this is very well suited to doing a random version. So the random divergence is, instead of picking the worst case scenario, so you're picking, so the divergence measures the worst case scenario, the worst points, the points that are the hardest to connect outside a ball. The random divergence is you pick the 2 points at random instead. Okay, and then you can measure again what's the minimal length of a path. And so the theorem, so this paper went on archive, I think last week. Again, let's say the informal version. So we can say something about relatively hyperbolic groups, maybe finitely presented relatively hyperbolic groups, so in particular hyperbolic groups. But okay, in that case, maybe it's not so interesting. We can say something about right angle arcing groups, and we can say something about mapping class groups. And there would be other examples that we can say. What can we say? Something that we were not very happy about, which is that the random divergence is equivalent to the divergence. So it's not really a new quasi-isometry invariant in those cases. But it's an interesting fact still, because so it tells you that the divergence of 2 random points is kind of as bad as it can be.
So quick comment. I mean, your divergence function, right? I mean, if it grows faster than linear, then it grows exponential, right? No, there's actually lots of examples where it's quadratic. So for mapping class group, it's quadratic. In this case also, it's, well, okay, up to except if it's a product or if it's a free product, and it is also quadratic. And yes, and here it's exponential. Well, you know, a long time ago, I defined a similarly defined function, probably a little different than yours. And there it was that it's either, you know, linear.
Yeah.
Or...
Yeah. So for this definition, there was actually an open question for a while, whether it was linear or exponential. But yeah, it turns out that you can realize all polynomial degrees, for example. Yeah. Okay. So yeah, I mean, it's an interesting fact, maybe not what we were hoping for, because it's not a new QI invariant, but still hopefully interesting. And I mean, it was worth trying. And then, but yeah, so let me mention that like 2 days after the paper went on archive, we got an idea for how to make a group, which is actually a small cancellation group, infinitely presented small cancellation group, where the random divergence is much smaller than the divergence. I mean, it is smaller than the divergence. So let me call it a statement, because not a single line of the proof of this is written. So the statement can be true or false up to now. I'm confident. I mean, I'm reasonably confident that it will be a theorem in the future, but we will see about that. And interestingly, in this case, actually, the random divergence can be computed, and the actual divergence, we don't know how to compute it. We can only get a bound. So there's also the idea that maybe the random QI invariant can be computed more easily in certain cases. All right.
Your statement is like a random theorem, right? I mean, that as opposed to being false. True.
Yeah. Okay. Yeah, and that's all I wanted to say. Yeah, look at Markov chains. Thank you.
Okay, thank you very much. So let's thank our speaker. And let me open the discussion. So any comments or questions?
Alessandro, you mentioned that every polynomial degree can be realized. Is that part of your result, or is that something independent or even due to someone else? Didn't catch that.
That the polynomial degrees of divergence can be realized. So that's result of Makura and Verstock-Drutu, and they are actually there are, I mean, they're very reasonable groups. They are cat0 groups, and right, and in fact they can even be realized within right-angle Coxer groups, so all polynomial degrees of divergence. That was proven a bit later. Yeah.
Okay, thanks.
Sure.
Yeah, let me make a comment, yet another comment. Actually, you know, some years ago, one of my students, Jeff Lindquist, actually dug out this paper by White that you mentioned.
Yeah.
You know, we observed that, you know, in many cases, you can promote a quasi-isometry actually to by Lipschitz map. And actually, at the time, I got very excited about this because I thought, well, maybe one can somehow use this to do something with Markov chains.
Oh,
but,
you had that idea. Okay.
Yeah, no, we had this idea, but we never pursued it because, you know, it wasn't to me clear what kind of by Lipschitz invariants you can define for Markov chains, actually.
Okay.
So maybe one should think harder about this whole problem. You know, if you have Markov chain and have a by Lipschitz map, are there some kind of very general invariants that you can get out of this? Yeah, this I think would be suggested by your work.
Yeah.
I mean,
Yeah,
he at the time proved some deterministic things. I mean, for example, there's this curious fact that if you take two regular trees, for example, you know, with different vertex degrees, they are, if you just restrict, if you just look at the vertex set, they are by Lipschitz equivalent, which at first sight is very surprising, right? If you think a little bit hard about it, it's not so surprising anymore. But you know, at the time, we were quite puzzled by these.
Cool. It's yeah, interesting that yeah, I mean, to be honest, I was wondering if anyone had thought about this, and yeah, I couldn't find anything much in the literature.
Well, I mean, I was just looking it up during your talk. I mean, there is an archive preprint by my student Jeff Lindquist, but you know, he doesn't talk about any kind of random walks and things like this. Yeah, but we definitely had this idea at the time, but
nice.
Didn't know what to do with it.
Nice.
Okay, so are there other questions or comments?
Yes, I have one question or maybe two. So do you have some results on Markov chains on SL2R or other Lie groups?
So I haven't thought
about... I imagine that SL2R, maybe it's a parallel theory that you developed, maybe?
Right, so I haven't thought about non-discrete groups at all. So I'm not, yeah. I wouldn't know, yeah, it's probably worth investigating, but I don't have anything specific to say about that.
But so far there's no like analog of like Furstenberg theory or something like that for Markov chains, not just random
like
walks.
Boundary theory of some, right? So
yeah, something like that.
So yeah, there I would say no. So I've been told by people who know way more than me about this, that boundary Poisson boundary can be defined for Poisson boundary can be defined for Markov chains, but
or even simpler questions like the COT for random matrices, for instance.
Right. Yeah, I don't. Right. So I mean, I should say that the CLT does not hold for Markov chains. Actually, let me even write it. So Markov chains are not so tame, like are wild. So there's actually I think it appeared just this morning. So again, Gaussbra and Spinden show that in fact there exists a tame Markov chain, like in the as defined above. I mean, as not defined above. Sorry. So one of the ones that we are considering, such that, so one basic result about random walks is that you look at the expected value of the distance from the identity, and you divide by n, and this is a limit for random walks. But so this limit does not exist. So they have so it is a Markov chain on the free group. So it's nothing crazy. And they have an example where the limit exists, but the CLT does not hold. And also some so I think that this one, so the other example not, but this example can be really obtained by explicitly by the push forward of the simple random walk on F2. So it's interesting that you can you know, right, there's a there's a limit to what you can prove on the Markov chains. It's interesting that you can still use them to prove a CLT, just via something else though.
I have a question on this theorem 3, which was the first one that you presented.
Yep.
Suppose instead of jumping uniformly, you have some probability of jumping to different generators. Do these parameters L and sigma depend continuously on these probabilities?
Yeah. So right. So there's in this paper we also study that problem, and the answer is yes. If you formulate it, I mean, but you can formulate it in different ways. So we formulate it in some sensible ways, and the answer is yes in those cases.
Oh, okay, thanks. And also, you mentioned the sublinear tracking of this random walks. Does your result imply that this tracking is actually about the order of square root and deviation from the geodesic?
So I can tell you exactly what the statement is. So the okay, there exists. Okay, let me write the quantifiers later. So you look at the probability that at the kth step of the random walk, you're far from the geodesic. So distance from a geodesic connecting the endpoints. So you look at the probability that this is large, and this decays exponentially in this parameter measuring large. And so I guess there exists C for all k less than n, and for all t. Right. So in picture, so you have the geodesic connecting the endpoints. Then you have the kth step, and with large probability, the kth step is within some bound of the geodesic.
Okay. So you have some kind of exponential tails for the deviation.
Yeah. Right.
But the central limit theorem suggests that you might even have Gaussian tails, or maybe that's too much.
No, I think that's too much. Yeah.
Okay.
So right, actually, so with Matteo, we deduced the CLT from I think we just needed the expected value of that distance square. So this is square. Yeah, I think that should be enough. Implies CLT. So this is bounded independently of k, less than or constant. Yeah.
Thanks.
Well,
Sure.
okay, so